Welcome CTM students and anybody else who might be watching to the lesson for 5.7. We are talking about arithmetic and geometric sequences in this lesson. For some of you CTM students especially, this should be a review from you or for you from Algebra 2, some stuff that you learned in Algebra 2. But if you're new to this or if you're not new to this, either way I'm going to treat it as though you've never seen this stuff and try to teach it in such a way that you would get it whether or not you've seen it before. Okay, so let's get started. Let's get into the lesson and start talking about first what it starts off with, arithmetic sequences. We're going to talk about that first. So let's put a big heading. And how about not in yellow? That would be a good idea. There we go. Big heading of arithmetic sequences. So this is, you could say, part one of two major parts in this lesson. So first of all, maybe you never learned or maybe you forgot what an arithmetic sequence is. We're going to learn about that in these first couple of examples. Remind us what that is or see it for the first time. So write the first, we're going to go 5 terms. Write the first 5 terms of the arithmetic sequence. With first term 2 and a common difference of 3. And so SOLN, that's our solution, shorthand for that, solution. What are we starting with? Our first term is 2, so the sequence would begin with the number 2. Put a comma, and then we're going to put our second term, and so on. Second term, third term, fourth term, all the way up to the 5th term, since we're looking for the first 5 terms. A common difference is 3. That means the difference from one to the next is a positive value of 3, positive 3. So 2 to the next one, I should be adding 3 to that, I would get 5. Keep that pattern going, add 3 more, I get 8. Get 11, and the 5th term finally would be 14. So this is our sequence with the first 5 terms, and this would be my answer. That would be all I have to do for something like that. A few things though I want to make notes of on this one. Let's call this what it is. It's A1. This is the first term. They use the letter A. I'm not exactly sure why it is that they chose the letter A, but that's what they've chosen for sequences. Then that's what we're going to go with too. So A1, A2, A3, A4, and A5. Put that in the different color for me if you're one of my students, please. And then this one, as we go from one to the next, the common difference was 3. That's what we did. We added 3 from one to the next. So put that underneath it as a good reminder as to why this was what it was later when you look at this. And one other thing I want you to underline, or doing a different color here, this common difference. What is a common difference, or why is that important? So we know the common difference, it's a positive 3, we're adding 3 each time here, but this is what makes it an arithmetic sequence. So I'm going to underline arithmetic here too. Let's put that underline there. This is what makes it an arithmetic sequence. If it was a common ratio, we're going to talk about that later. If it was multiplied by, instead of adding something, adding and subtracting, they go together. Multiplying, dividing, they go together. So common difference versus a common ratio, we're going to see the difference there. And if you are a visual learner, I decided to put this over here for you. Hopefully you find this helpful too, so you can notice you don't have to draw the picture, but it's here every time. Plus 3, you're going to get 5. Plus 3, you're going to get 8. This is like a stack of coins, something like that. So if that helps you, that's also what's going on there. Sometimes we're adding a negative value instead. So it's not always going to be growing. Sometimes it'll be shrinking instead. You could even have negative numbers too. So we're going to see that in some of these further examples. But let's try out another. I guess this is our first big equation. We didn't have an equation yet. Sorry. Our first equation, the general or nth term of an arithmetic sequence. I know that looks like arithmetic, and that's usually how we say it, but when we're talking about sequences, we pronounce it arithmetic instead. At least that's how I was taught, so that's how I'm teaching it here too. Alright, so this is the big equation. This is the big guy, one of the 4 big guys for this lesson. That a to the n, or a, not to the n, but a sub n equals a sub 1 plus n minus 1 times d. Now, what does all this stuff stand for? That's all fine and dandy if you remember that, but if you don't know what these things stand for, you're out of luck. This right here, let's put this in the different color, and kind of underneath that, this is the nth term. Whatever term you're on, maybe it's the 7th term, the n would be 7. Maybe it's the 100th term, n would be 100. This right here is the first term. A sub 1 is always the first term. And we should know that based on this, it's the nth term, so whatever n is here would be the same as it is right here. In this d, this is an arithmetic sequence, this is the common difference. I don't know if you hear some music in the background there. I'm going to have to just record despite that. They've got some stuff going on during lunch. I'm recording this during lunch today. Ooh. So we'll have some music in the background to listen to very, very faintly as I record this today. So example 2 is to do this, to find the, I'm going to go kind of crazy here, the 139th term. And I decided to do that so you didn't think, oh, I'm just going to add 2 or whatever the difference is 5 times and I'll be done. I don't have to know this formula. I don't ever have to use this formula. If you're going to add 2 139 times, so yeah, have fun with that. You go ahead and do that if you want. You might end up looking like me after you do that. Notice, come on, there you go. You might end up looking like me. You see this? This is what happens when you try to find the 139th term without this equation. You just keep adding the same thing 139 times, and you start going like this because you're so frustrated. Yeah, don't want that to happen to you. So I'm just trying to think of your good in all of this. So find the 139th term of the arithmetic sequence. Oh, did you see that too? Right there, Michigan basketball, what's up? Gotta represent. Woo-hoo! I'm dating myself by showing you that shirt. Yes, we're in the Final Four! We're in the Final Four! Woo! It's been 20 long years I've waited for my team, Michigan, to be in the Final Four again. So, let me get back to the math problem. Whose first term is 26 and whose common difference oh, somebody's doing really bad karaoke out there, it sounds like, and whose common difference is -8. Alrighty, hopefully that's not one of my students that's going to come and say, that was me singing, Mr. Wagner. I sing really well. No, okay. I'm sorry. Truth be told, it's not sounding too good. Maybe it's because the walls are in the way and it's all muffled and it sounds bad. But this is going to be n. This is going to be a1, your first term, and this is going to be your difference. So let's label those things. 139 is n, 26 is a1, and d as -8. And now it's just a matter of plugging those things in to this formula. So a sub n, let's just write the formula down one more time just to make it easier to see where the next step came from. So this is a of 139 was equal to the first term, 26, plus the n value is 139. We're talking about the 139th term, and we're subtracting 1 from that. The reason why this works, why we subtract 1 just very quickly, is that if we just left it as n, the first term you'd actually be adding something to the first term. We're not supposed to add anything to the first term, so I got 1 minus 1, which is 0. 0 times anything is still going to be 0, so I'm not adding anything to the first term with n minus 1. That's why it's n minus 1 instead of n. but this would be times the common difference times -8. It's not this minus 8, it's this times a -8. So make sure you use parentheses there. And here we'd have 26 plus 138 times -8. If you multiply 138 times -8, you end up getting -1,104. And then 26 minus 1,104. As we should have expected, we were going to get negative pretty quickly here. After the first 3 terms, we're going to start to get negative there because you'd be taking this minus 8. The second term would be 18, and then 10, and then 2, and then -6, and so on. So -1,078 is how many, or what the value would be of the 139th term. But again, I didn't want to take this minus 8 139 different times. It would actually be 138 different times because that's my first term. Yeah, that would be again where this comes from. You don't want to do that. It's no good, not at all. Example 3. So we're going to use that same formula, but we're going to write an expression for the general term is the same as the nth term, or nth term, a sub n. And I'm wording it just like the book does, just so we get used to that phraseology, phrasing, the way it is phrased. For the sequence, the way it's worded, how about that? The sequence -5, -1, 3, 7, and 11, and that pattern I'm going to say is going to continue on and on, so I'll put a ... right there. Okay, so my solution, leave a line of space in between here. We're going to write some stuff right there, so I'm going to leave a line right there, but my solution, I got to go back to that equation there, so I'm going back to this. I'm going to rewrite that. So a sub n equals the first term plus this n minus 1 times the common difference, because we're going to be adding n minus 1 times however many terms that we have will be filled in with n. The common difference, though, what is the common difference here? If we look at the values, it looks like we're adding how much each time. This is a common difference of 4. Add 4, add 4, add 4. It's the same from each step to each next step. It's always adding 4. This is let's write this in a different color here, that this is A1. So this number right here is going to get plugged in right there. And then notice that you're adding 4 each time. This is your A2, this is your A3, A4, A5, and so on. And then notice each time we are doing plus 4. So you can to find the common difference, you can take any 2 values you want in this, as long as it's an arithmetic sequence, so as long as it's the same thing being added or subtracted. Adding a negative is the same as subtracting. So as long as it's the same thing being added every time, and you know it's arithmetic, then you know this common difference is going to be going in right there. So the common difference here, it's a positive 4. That means a sub n in general would equal -5 plus whatever your n value is, or minus 1, times this common difference is 4. And then at that point we would distribute the 4. Let's show that in a different color. Sometimes, or I guess we're used to seeing, most of the time I should say, we're used to seeing the 4 on this side, or whatever the number is, distributing that way, but just because it's on the right side doesn't matter. You still distribute it through. You have multiplication like this. So this would be -5 plus 4n minus 4. We can combine like terms, one more step there. We've got -5 minus 4, that would be -9. So I have 4n, I'm going to write my variable part first, minus 9 from there. And that, my friends, is your final answer for that. Or I should say, so, in general, the nth term, you would just plug in n into this equation, and you'd have your number. This expression, this 4n minus 9, that part is going to give you what that is. Could you use this up here instead? Sure, but this is a kind of a simplified version of that based on the values we have here. Let's check out one more example for arithmetic sequences. I almost said series. Series is a different thing where you talk about the sum of no matter how many terms you have, how that works. But this is, we're not going to talk about series in this class. We're just talking about sequences. So the sum of the first n terms, I guess this is kind of an introduction to series with this example, but this is a sum of the first n terms in an arithmetic sequence. And we'll talk about where this equation comes from and why it works in just a little bit, but for right now, just write it down. It's the s of the n, s standing for the sum of the first n terms. So s of n is going to be n times the first term plus the last term, a sub n, all over 2. Okay, so S stands for sum here. Here's your example. Here's what we're going to do in this one. Find, not first, find the sum of the, here's my first, of the first 100 natural numbers. Natural numbers are those whole numbers, but it can't be 0. 0 is included as a whole number, but natural numbers don't include the number 0. So your solution here, well, first of all, let's determine what sequence this is. This is the sequence that goes from 1 to 100, just a difference of 1 each time. This is the sequence 1, 2, 3, 4, and so on. So dot, dot, dot. I'm not going to write all the numbers from 1 to 100. That would be ludicrous. No thank you. This is that sequence, so that pattern continues all the way up to 100. In this sequence, you have, using or thinking about this equation right here, what do I need? I need a1. I need my first term. That's 1. What's my a sub n? My last term, my a sub 100. Here is 100. And the common difference, I guess I don't need that here. The common difference is 1, but I don't need that in this equation. I do need what n equals, though, and n equals 100. There's 100 terms. And so we could say, therefore, sum of the first 100 terms, s sub 100, is going to equal, let's plug it in, your n is 100, your a sub 1, first term is 1, your last term, a sub n, is 100, and then that all over 2 is going to give you your answer. This would be 100 times 101 over 2. This would be 10,100 over 2, which would equal 50, 50. Okay, so I think it's nicer, though, if you actually know where formulas come from. They're a lot easier to remember if you can do that, and I'm going to quickly show you where this formula comes from or why it works. So this guy, this is, I just slashed his face right through right there. This guy is, that's a little better. I still got his chin there a little bit. This guy is Gauss, Carl Friedrich Gauss, brilliant mathematician, sometimes called the Prince of Mathematics. And when he was 10 years old, his math teacher was like, I need to keep you guys busy for a while, so okay, kids, you're going to add the numbers 1 through 100. Add the first 100 natural numbers, the first 100 whole numbers, except for 0, hello bell. And so that's what he did. He was like, I'm going to keep the kids busy for a while. I can get some work done. These rugrats can stop whining and complaining about things in my ear. I don't know what he was doing exactly, why he did that, but Gauss, the little mathematical prodigy he was like, okay, I think I can do this without a calculator pretty quick. He made him do it without a calculator because, well, it was the 1800s and they didn't have calculators back then. So here's what Gauss thought about. Okay, this is 1 plus 2 plus 3. Again, you don't have to write this down. This keeps going. 98, 99, and 100. This is just a little FYI here. But if you look at this and you add up the first one and the last one, and you add up the second one and the second to last one, and so on, they're all going to add up to 101. And you have 50 pairs of 101. That means the sum is going to equal 50 times 101. In other words, it's half of 101, or half of 100, which is how many numbers you have, times the first and the last added together. Well, look at that. Here's the first one and the last one added together, and you add half of the number of terms you have. That's where this equation comes from. So this is 5,050. Nice job, little Gauss. He doesn't look so little here anymore, but when he was 10 years old, he figured that out in a matter of moments, told his teacher, and I think from that moment on, he was bound for greatness mathematically. But let's check out now geometric sequences at this point. So geometric sequences, this is kind of like part 2 of our notes here, geometric sequences. And very, very similar, a lot of similarities between this and what we just did. So I'm going to keep the examples looking more or less the same, except we're going to see the difference between arithmetic now and geometric sequences. So here, write the first 5 terms, just like I had you do in example 1, but now with a geometric sequence. Write the first 5 terms of the geometric sequence whose first term is 3 and whose common ratio is 2. Our solution to this, well, let's write our first term first. Imagine that. First term is going to be 3. It's the first term here listed. The common ratio now is 2. Let's underline this in a different color. Common difference, that's when we just added something. It could be adding a negative, same as subtracting. Now here, a common ratio instead is what's going to be making it. This makes it, write this down for me, my students, makes it geometric. Why am I writing arithmetic? I've got arithmetic on the mind. Makes it a geometric sequence. So common ratio, think of multiplying things. Multiplying things is the same as dividing in a sense, because multiplying by 2 would be the same as dividing by 1/2. If you were multiplying by 1/2, that's the same as dividing by 2. We can just kind of take the reciprocal of those things for division instead. And so 3, common ratio is 2. We're going to take that number and just multiply it by 2, since that's the common ratio. So 3 to 6 to 12, keep multiplying by 2 to 24, and finally to 48. This would be the 5th term. I'm not asked for anything beyond 5 terms, so I would stop right there. And so this would be your answer for a question as this is. And in your different color, let's put this here. This is your A1, A2, A3, A4, and A5. We still use A's for these terms, so first term, second term, third term, and so on. The difference between this and the arithmetic series or sequences was that we were adding something here. Now we're multiplying by something. So it's not a common difference, it's a common ratio instead. That ratio is 2. So it's multiplying by 2 every time. And that pattern holds here, times 2, times 2, times 2. And for those of you that are visual and like to see visual things, this is 3 right here. If I multiply that by 2, you don't have to write this part down, but multiply by 2 and you get 6, and that's what it's showing here. It doubled the stack. Multiply this by 2 and you get 12, and so on. If you just didn't have enough room for 24 and 48, it's going to get bigger a lot quicker than the arithmetic series sequences. I keep saying series, but sequences instead. Alright, now the same thing as before, but now for geometric series sequences. sequences. We are not talking about series right now, Mr. Wagner. We're not talking about adding infinite series or stuff like that. Maybe you remember doing that if you were a former Algebra 2 student, but we're not getting into that right here. So a general nth term of a geometric sequence. You said it right. Good job, Mr. Wagner. Thanks. Thank you very much. So we have a sub n equals, you take your first term, and we're multiplying it by the ratio to whatever power that is, but if we multiplied by the ratio first, so multiplying a sub 1 times a ratio, that would give me the next term where I'd want my first term. So just like before we had n minus 1, same thing here, because I would want this to be, if this was my first term, I would want the power to be 0 so that the ratio to the 0 power would equal 1 so that the first term wouldn't change. So this is what our formula is. The R is the only thing that's different here than what we had before. The R here stands for the common ratio. So please label that for me. Everything else is the same as before. Example 6 then is going to use this to solve for this. So find the ninth term of the geometric sequence whose first term is 12 and whose common ratio is -3. And here is my solution for that. So we're talking about this formula right here. Let's write that again. A sub n equals the first term. So the nth term equals the first term times whatever the ratio is to the n minus 1 power. Right here is your n. It's the ninth term. This is your n value right there. So let's put that in a different color right next to that. And first term is 12. That's your first term. That's your a sub 1. The common ratio is a -3 in this case, so that's going to be my r. Alright, so we'll put that all next to that there. I'll just put that down here. It's okay if you wrote it there, but just didn't want to make it look like a power, like 3 to the -3 to the r power. That's not what we want. So a to the a sub 9, the ninth term, is going to equal the first term, 12, times the ratio, -3, to the n minus 1 power. N is 9, so I'm going to plug in 9 minus 1 right there. Now this would equal this times -3 to the 8th power. If you plug in anything to a positive power, even if it's negative, it'll change to a positive because you'd have an even number of negatives, which would cancel each other out. So 3 to the 8th power is going to be 6,561. Multiplying 12 by that value gives you 78,732. So notice this goes up very, very quickly. Even if the ratio is not all that big, like a -3, or the absolute value of that ratio would be +3, even if that's not all that big, like 3 doesn't seem like it's that much, but you start at 12 and you get to 78,000 in a matter of 9 terms already. So pretty big jumps here. You're going to notice a lot faster growth with stuff like this as long as the ratio is fairly big or even somewhat big or even not even that big, like 2 or 3. If it doubles or triples, it's going to grow really, really fast. Example 7 though. Still going to use that formula that we just had there. We're going to write an expression for the general or nth term a sub n of the sequence 2, 8, 32, 128, and so on. So dot, dot, dot. I'll just write the first 4 terms on this one. And what's our solution to that? Leave a line or 2 space there. And let's take a look here. So in your different color, let's label these. This is A1, this is A2, A3, A4, and so on. Is there a common ratio? Are you multiplying by the same number every time? So it looks like times 4, times 4, times 4. I see a common ratio there. So every time we're taking this times 4, that's the ratio, the common ratio. My formula is a sub n equals a sub 1 times r to the n minus 1. So I'm going to just write that in general one more time. This times 4, that's what's going in for the ratio right there. And then this 2, that's my a sub 1, that's going to get plugged in right there. So let's make little notes of that. This will be a sub n. Any term can be found using this formula 2 times, the ratio is 4, so I'm going to plug in 4 to the n minus 1. And this, there's really nothing you can do to simplify this, so we can leave it just like that. I wouldn't really need the parentheses there, so if I wanted to, I could write it like this as well, 2 times 4 to the n minus 1. And I can't put together the 2 and the 4 because they would have to have the same power. 2 is not to the n minus 1 power, and so I have to keep these two things separate. If they don't have the same power, I cannot put them together. That's a property of algebra there, property of powers. So the powers are different, got to keep them separate, but it would look like that. So if you knew what term you wanted to get, let's say you wanted to get the 10th term, you would just plug in 10 for n, and boom, it would give it to you right there. You just plug in 10 for n right here, you take 2 times 4 to the 10 minus 1 power, and that would give you your answer. We're going to do one more together here, and one more formula. So there were 4 big kahunas, big formulas in this lesson. This is the 4th of those 4 formulas. So the sum of the first n terms in a geometric sequence. Just like there was a formula, an equation for the sum of the first n terms in a arithmetic sequence, same thing is true about geometric sequences. That formula is this time, so it's a little more complex looking, I think, but a sub 1 times 1 minus r to the n over 1 minus r. So a little background on where this comes from. You don't have to write this down, but I do want to point this out to you. Again, if you can understand where something comes from, I think it's a lot easier to remember. So here's the quick proof of that. It's already listed or written here. This is another way to write the sum of the n terms. You take the first term, a is your first term, and then that would be like a times r to the 0 power would just be a. And then the second term would be a times the ratio to the first power, a times the ratio to the second power would be the next term, and so on, all the way to the n minus 1 power. This would be the first n terms of your ratio. If you multiply both sides by r, it would look like this, and then you could distribute the r through to everything here. That's what they did here to get this next. And so the powers went up by 1 every single time. And then if you took this whole thing right here, s sub n, and you took this whole thing right here, and you combine those together, you're going to have this. Let's see what we got here. And we take those and subtract that. So this minus this, that would change everything to minus signs here. The AR to the 1 would cancel. The AR to the 2 would cancel. The AR to the n minus 1 would cancel. All you'd be left with would be this first part, the A, and the last part, A to the R, N. And so we'd have this. There was a minus sign out in front here, so this would change to a minus right here. A minus A sub R to the N. And so you can pull out an S sub n here, and then divide both sides by 1 minus r right here, and boom, there's your formula right there. Am I going to make you prove that in class? No, probably not. But that's where it comes from. Don't just think that somebody made this up one day and was like, oh, this actually seems to work, I'm going to use this. No, you can prove it's true. So there's the proof right there. The proof is in the pudding. This looks like tapioca kind of, that color. Sounds good right now. I'm kind of hungry. It's lunchtime. I'm ready to eat. So find the sum of the first. We're going to go with 7. The first 7 terms in the geometric sequence. Fancy that. It's going to be geometric sequence because I just gave you that formula. So here's an example that uses this formula. Whose first term is 6 and whose common ratio is, this time we're going to go with 0.5, or 1/2 in other words. Let's label our parts here. Let's write down the formula first and then we'll label our parts. So the solution, let's write the general formula again, so S. So then the sum of the first n terms is geometric sequence, first term times 1 minus r to the n power over 1 minus r on the bottom. And so what's what here? The first 7 terms, this is your n. Your n is 7. And whose first term is 6, that's your a sub 1. And the common ratio is 0.5. There's your r. This is multiplying by 0.5. That means it's going to keep getting smaller and smaller as I multiply to the next term and so on. And so we'd have 6, and then multiplying by 1/2 for the second term would give me 3. Multiplying by 1/2 again would give me 1.5, and so on. So this should not be a very big value, actually. When you have ratios that are less than 1, you're going to be getting smaller and smaller as you go in terms of the absolute value. If the absolute value of the ratio is less than 1, it's going to keep getting smaller, the terms, and your sum will not keep getting bigger and bigger. This is actually a finite series. If you kept it going to infinity, it would have a finite sum. You learn more about that when you talk about series. So this, though, is going to be 6 to the 1 minus, and then r, your r is 0.5 to the n power. I'm sorry, I shouldn't have closed my parentheses there yet. N is 7, so that's going to be to the 7th power over 1 minus 0.5. So again, this is 0.5 to the 7th power, not 0.57. I'll try to put that up there. Let me put that up there just a little bit higher to make sure that's totally clear. So this is a 7th power up there. Now this is just a matter of working this out in a calculator. I wouldn't think you'd want to do 0.5 to the 7th power in your head, or even working that out on paper. Not much fun. So we get this. I'm going to leave it as an exact number for right now. That was the exact value my calculator gave to me. So 0.0078125. This is all going to be over 1 minus 0.5 is 0.5. Multiplying this, or subtracting this from this, first of all, would give you 0.9921875. And then finally taking this, putting this times this divided by a 0.5 in a calculator gives you 11.90625. So what is this formula actually doing, or really doing for you? Well, I think it's saving you a good deal of time, especially as n starts to get larger and larger. Don't write this down. This is just, unless you really want to, this is just a quick check to see that this worked out and to just describe to you how this works. Why does this work this way? So our first term, a sub 1, was 6. Our second term, multiply that by 0.5 and you get 3. Our third term, multiply that by 0.5 and you get 1.5. The fourth term, multiply this by half, or 0.5, and you have 0.75. The fifth term, you get 0.375. The sixth term, you get 0.1875, and the seventh term, you end up getting 0.09375. Now, that was cumbersome enough I did that all I work in a calculator beforehand when I made this video, but if you add all these terms together, that's what you get right there, 11.90625. And so as this n increases, as this number of terms increases, maybe you're doing the first 47 terms instead. Would you want to do this and keep doing that for the first 47 terms? Heck no. No way. Don't want to do that. That's why the formula is so beautiful, why it's so wonderful, so amazing. Yes, I'm talking this way about a formula, a theorem that's been proven. Math really is beautiful if you appreciate it for its intrinsic value. I think you've just become a better person right there. That's all. That's all I have. This is it. Last example. Example 8 is what I got. There's 10 more examples in the book. Check those out if you need some extra help as well. And good luck. Do well on your classwork here. See you guys later.